Hi students, this is Miss Fisher, and I promised I would give you a little bit of help with question 4, for response question 4 in your AP packet, where there's potentially some tricky geometry stuff going on. So let's do a little talk through. I'm not going to do the whole problem, but I'm going to get you started so that you know how to think about this one. Part A is totally doable, but I should point out something in Part A. They give you the equation. So we mentioned that this was a related rates question. And the nice part here is that they actually give you the equation that you're going to use. Well, you could have come up with a volume formula for a sphere. The issue is that it's a hemisphere which is just cut in half, but it's being filled up. And so what they've done is they've come up with a formula magically that has height in it and radius, but the thing that they've done is they've managed to come up with a formula in which your radius in the formula, this big R, is the constant radius. So you have two radii in this problem. You've got the constant radius of the hemispherical bowl, and then you have the changing radius of the water level, or the circle of water. Depending on how big that is or how full the bowl is, that radius is going to get bigger and smaller. So what they've done is they've come up with a formula with just the big R being defined as that unchanging radius. And you don't have to worry about the little r in that particular part. So go through your typical process of using the related rates process, implicit differentiation, substitute in what you know, and you don't actually have to do a change of variables there or solve for one variable in terms of another. Okay. Now when you get to Part B is really a setup for Part C. So let's take a quick look at Part C. And if we look at Part C, they're asking how fast is the circular area of the surface of the spherical segment of water growing in square inches per second when the water is 2 inches deep. A lot of times I kind of cheat when I'm doing related rates problems. And to figure out what I'm trying to find, I look at the units. So they're asking me to find something in square inches per second. Well, I know square inch measurements measure area. So I must be looking for dA dt, which means I need a formula for area equals. And then I can look for dA dt. That's going to be my answer here. So how fast is the circular area of the surface? All they're looking for is this right here. They're looking for what's the area of that and how fast is that area changing. Obviously, it's getting bigger as my bowl gets more filled up. So area of a circle formula is really what we're using here. And it's as simple as area equals pi times radius squared. So formula is not hard, but we're looking for dA dt. If you take a look at the right-hand side and just imagine taking the derivative there, you're going to end up with a dr dt. Pi is a constant multiple, but r is a variable. This little r is not my 6. That little r is that radius that's changing that we talked about. So that's where we need to do some work to substitute. We basically need to get rid of this r and replace it with an expression that's equal to changing radius, but is in terms of capital R, which is constant, or we could use h, because we will have, based on our answer to Part A, we will have the rate at which the water level is rising. We're going to have dH dt. So Part A is asking for dH dt, and you could use your answer to dH dt if you need to. Okay? So that's what I'm going to do now, is kind of walk through Part B with you, now that we have a little bit of a setup for that. So if we're looking at Part B, let's see if I can give myself some more room. You know what, I'm just going to try to redraw that on another page. So give me a second to redraw. You might want to do this on your paper. I'm just redrawing that hemispherical bowl that we're looking at. And it's not going to be a great picture, but I've got center up here, center of my circle of intersection, the water surface. And I'm not actually going to draw the radius across this time. One of my students that participates in Math League summarized this. We were talking about problem-solving strategies and summarized it very nicely the other day when he said, when you're solving a problem that involves circles, any kind of circles, you should always, always, always start by drawing in a radius. And this problem is almost exactly like one that I do in my geometry classes. We're just not answering the same question, but they have to essentially draw the same picture. So instead of drawing my radius straight across, my radius, which is equal to 6, I'm going to draw that radius in, but I'm going to draw it somewhere else. So I'm getting rid of that. And I'm going to draw it, remember, from this point out to any point on my sphere is going to be 6, going all the way out to the side. So the one that I'm going to choose to draw in is I'm going to go to this point down here. And that is, oops, that is 6. Because that is my capital R, which we've already defined in the problem as 6. Now, why did I draw that? Because this is little r down here. And then if I draw, one more thing into my picture, so let's grab one more color. If I draw the height in there, now be careful, I'm drawing the height of that little triangle. Now let's see what else we know. We know that this entire thing, if I draw down to here, is a length of 6. And we know that we've defined this bottom half, I say half loosely because it's not necessarily half, as my height. So that's only this part here. The height of my water level. So we've used h for that, and if we use that, we can come up with that green piece. An expression for that would be 6 minus h. Again, it's the whole length, which is 6, or big capital R, and my height is changing here, so I can't just subtract a magic number and say it's going to be a certain number, but this is always going to be 6 minus whatever my height is. And now, if you can kind of look beyond the mess that I've made of this problem, I have a right triangle. Let me highlight it for you here. And I'm going to go back to my geometry of Pythagorean theorem, and I'm going to hopefully solve for my little radius. So let's keep going. I'll get you maybe started on this step and then get you to part C. So we can, or you can stop the video right now and try this on your own if you're feeling like you can do it. So I've got my little r squared plus my 6 minus h squared is equal to 6 squared, and remember that was my hypotenuse, my big radius that's not changing. And from here, I'm just going to go ahead and simplify, and I'm going to have to do some work right in here because I've got a quantity squared. So remember, that's not going to be 36 plus h squared. I've got to expand that binomial. So it's going to be 36 minus 12h plus h squared. If you're not seeing that, multiply it out this way, and you should see it. And that's going to give me, now I'm finally ready to combine my like terms. So if I combine my like terms, I don't have any like terms. I take that back, just my 36. So let's solve for everything in terms of r squared. Or solve for r squared, I'm sorry. Put everything else on the other side. So I'm going to move all three of these terms over to the right side. So I'm going to have a negative h squared, a positive 12h, and a 36. I'm subtracting 36. Okay, the 36s are gone. So that's nice. It might look a little better to you if you write it this way, 12h minus h squared. We don't usually like to have a negative h squared term. And then I'm going to take the square root of that. So there we have it. I've solved for radius, and that's actually the question for part B. Find an expression for r, the radius of the sphere of the surface of the spherical segment of water in terms of h. So in terms of h, because I've got an h in my expression there. So that would be your answer to part B. And now I'm going to suggest that you go back to the formula we had for part C, area equals pi times radius squared, and substitute in this part and for your radius. And now you have something that's in terms of h. You're going to get a dH dt when you take the derivative of it, and then you'll be able to use your answer for part A to go ahead and finish the problem. So good luck with that. I'm going to leave you there and let you try the rest of it.